data scientist or engineer and educator. He is currently a data engineering consultant in AIA Philamlife. Apart from his main work in the industry, he does research and teaching as part of his faculty work in the LSU. For his academic background, he took up a master's in data science at the Asian Institute of Management, where he graduated as batch salutatorian with high distinction, the highest academic award, and Bachelor of Science in Computer Science major in Computer System Engineering at De La Salle University. Let us all welcome Mr. Jude Michael Teves for machine learning using TensorFlow. Let us all give him a virtual round of applause.
Hello, everyone.
Hello.
Am I audible? Hello?
Yes, po, yes.
Okay, great, great, great. Okay, just give me a few seconds. I'm opening my slide deck. Wait a second. Before I start, I just want to have an idea about the background of the participants. Can you just comment in the chat about your experience in machine learning? I mean, have you done machine learning before, or anything about Python and machine learning, basically? So I can adjust my talk depending on the. Okay, okay. No, so I guess I'll take it slow then. Okay, that's understandable. I will. Okay then. Okay then. Oh, nice. Someone has used Keras and TensorFlow. I'll actually show something related to that later. But I believe this will be thoroughly discussed in the workshop part of this event. Unfortunately, that is not my focus. I'm just going to be talking mostly about general machine learning. Okay, I am now going to share my slide deck. Sharing it now. I have so many tabs. Wait, let me select the correct one. Okay. Can you see it now?
Yes, po.
Okay, great, 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 great. Okay, so yeah, I'll be talking about machine learning using TensorFlow. But before that, we'll be discussing high-level stuff about machine learning, because I believe not all of you have background about machine learning, right? Okay, so let's start things first. Who among you knows who this person is? Do you have any idea? Oh, who is this person? No idea, no idea. Actually, this is an image generated by an AI. Yes, that is correct. Thank you, Gerald. I hope I pronounced that correctly. Yes, this is AI generated. Cool, right? So you could use artificial intelligence to do these things. You could search for this person does not exist, and then it will generate those images for you. Images of people that are not real. How about you? How about this? I'm sorry. Who among you knows what AlphaGo is? Let me look at the chat. Do you guys know AlphaGo? This was created by Google, and this is an AI model that is able to beat the best Go player in the world, Lisa Doll. Just to give context, yeah. So someone has mentioned it in the chat. First computer program to defeat a professional human Go player. And Go, to give you an idea, is more complicated than chess. It's a very complicated game. And in the game of chess, just to give you some reference point, uh, it is estimated that it has so many possible combinations in the game that it exceeds the number of possible atoms in the universe. So that's how complicated it is. There's number of combinations, and Go is much more complicated than that. And Google is able to create an AI model that beats the best Go player in the world. Okay, here is something that I got from the internet about AI. Um, I'll just be reading this for you. So general artificial intelligence is going to happen a few years from now. There is now a reasonable amount of skepticism about whether AI will be an improvement on us. At present, its ability to generalize new situations is questionable. The challenges of language processing and scientific modeling are significant, while ethical issues are formidable. However, it is clear that today's AI systems are progressing at an extremely fast pace and that their numerical capabilities are increasing. Do you guys agree with this statement about artificial intelligence? What do you think about the statement? Okay, here's the funny thing. This paragraph is also generated by an AI. This is not human made. I just provided the first sentence here, and I let the AI model do the rest. So starting from there is now a reasonable amount of skepticism, and after that, those things are generated by AI. So we could also do these things using AI. And well, about general AI, honestly, I don't think it's going to happen a few years from now. We're still far from that, but that's just my opinion. Basically, we're hitting the limits of what we can do with the current architecture that we're using in artificial intelligence, but that's another topic. Anyway, we need a very different approach to solve general AI. So anyway, before I proceed, I would like to discuss industrial revolution. Do you guys know what industrial revolution is? Because this is related to what's happening in our um, society, why AI is becoming more and more relevant. Okay, great. So you guys know what industrial revolution is. So what is it? Can you type it in the chat? Let's see. Or you can actually speak if you want. I want to hear your voice as well. Who wants to share if you want? How would you describe an industrial revolution? Hmm, I see some responses. So the industrial revolution is the booming of ideas or innovation in relation to the current era's technology. Right, I agree with that statement. Industrial revolution is progressive, yes. And advancement, start automation of manual tasks. Yep, correct statements. Well, for me, I will describe industrial revolution as um, something wherein there's a massive shift in how we live our lives. For example, before Industrial Revolution 1.0, our society is mostly agricultural. So we plant and then we harvest our crops. But when Industrial Revolution 1.0 came, we harnessed the power of well, steam. And because of that, we're able to automate lots of things. So because of that, things got faster and basically we became more efficient in the things that we do. And the same goes for all industrial revolutions, 2.0, 3.0, 4.0. We're just making use of different technologies. In 1.0, it's steam engine. In 2.0, it's electricity. In 3.0, it's computers, it's transistors. Those are the basic blocks of the technology that we have. And in 4.0, it's the synergy of all these things. So it's not just about computers. Basically, you have lots of devices right now, but you have communications now. It has to be intelligent. They all have to communicate with each other so they can make better, um, basically better responses to what we're doing, because we built all these machines to serve us humans. So that's basically what's in Industrial Revolution 4.0, the synergy of all these technologies that we have created. And one key technology in Industrial Revolution 4.0 is artificial intelligence. And artificial intelligence is basically us imparting our knowledge to computers. So basically, we, as humans, are capable of doing lots of cognitive tasks, and we're trying to put that into computers. So they will be doing the same thing essentially. That's our goal in AI. So machines just mimicking us humans. If we can determine, for example, a very basic example of AI, and I'm sure most of you have seen this example on the internet. Is this a cat or a dog? When you see this image, that's something that we can determine as humans, and we would like the computer to be able to do that as well. So that's one example of AI. So at a very general sense, that's what AI is, and machine learning is one subset of AI, wherein we're making use of um, lots of data to train our A model. It's a very specific technique in AI. There are lots of techniques, but in ML, we're feeding it with so much data that it is able to learn those patterns on its own without us explicitly um, providing the rules. So in deep learning now, it's more specific than that. We're making use of a very specific technique in machine learning. We're making use of neural networks. Have you heard of neural networks before? So deep learning is essentially neural networks. You could interchange them. No? Anyway, there are lots of machine learning algorithms, and neural networks is one of them. And that's what's driving most of the advancements in the field of AI nowadays. When you see lots of advanced uh, programs, advanced AI systems, in most cases, they are deep learning based. So just to summarize things, AI is the bigger umbrella term. It encompasses all the techniques. Um, as long as you are trying to mimic something that we can do as humans, mimic the cognitive tasks that we can perform in machine learning, you're making use of specific techniques in AI wherein you feed a lot of data for it to automatically identify or map out the input to output pattern. And in deep learning, you're making use of a very specific machine learning technique, which is neural networks. So that's the summary of things. So yeah, um, and AI is working nowadays because of data. And I believe you've already heard of the phrase, data is the new oil. So why is data the new oil? Well, much like the oil companies back then, big tech companies who have lots of data, they're the ones who are rich. The oil companies back then, and like oil, you have to refine it, you have to process it for you to get value out of it. This is the same thing with data. You have, as it is, it doesn't have much value, but you have to do some pre-processing and lots of things for you to get value. So that's the analogy that you can think of when it comes to data and oil. And the thing right now is we have so much data like before. So that's why ML is working now. Again, as I mentioned earlier, in machine learning, you need lots of data. So back then we don't have much data, but as you can see, it's exponentially increasing. It is projected that we'll have 175 zettabytes of data by 2025, although the study was done back in 2018, but that's generally the trend. And how big is a zettabyte? It's 1 billion times 1 trillion. Very big number, basically. 1 billion times 1 trillion. What else? Aside from the increase in the data that we have, there's also the hardware aspect of things. So what you're seeing here is Moore's law, and I'll just be reading this here. Moore's law describes the empirical regularity that the number of transistors on ICs or integrated circuits doubles approximately every 2 years. If you look at this graph, that's generally the trend. And why is it important for us? Basically, if you have one chip, you have lots of transistors, and if you have lots of transistors, then that means you have lots of computational power. And if you have lots of computational power, then you could perform more complicated tasks. So back in 1970, we have about just a few thousands of transistors in a single chip. But right now, we're getting what? About, say, 30 billion transistors in a single chip. Right. So that's where we are right now. Although this is plateauing because of the physical constraints that we have when it comes to manufacturing ICs. Currently, if I remember correctly, the size of the smallest transistor is about 3 nanometers, and that's very small. Compared with the size of an atom, the largest atom is about 0.3 nanometers. So we're getting there. We're getting to the size of the smallest of the biggest atom, I mean. And we have to do a very different approach to increase the number of computational power of our computer systems, given that we're reaching the physical limits. Anyway, we have very good computers nowadays. That's a very critical factor why AI or ML is working now compared to before. And finally, we have research. I mean, if you have data and you have hardware, but you don't have the algorithms in research, then it's really pointless, right? So I believe this is one of the most influential papers in the field of artificial intelligence or machine learning. This is AlexNet. And all these people here, Alex, Zabsky, Elias Itzkever, Geoffrey Hinton, they are very popular in the field of AI. Geoffrey Hinton is actually one of the godfathers of AI. Anyway, in this paper, they have created this model that was able to beat the next best performing model by a big margin. And why is this successful? Why is this very important? I believe this is also one of the models that started hype in deep learning back in, I think it's 2011 or 2012. What happened was people started to believe in deep learning again because we are getting a performance that is near human level, unlike most AI models back then. And it was able to beat the next best performing model by a big margin, like 15% error. So this is a very good model, at least back then. Of course, right now there are lots of better models, but it's very good. And it also utilized GPU. It is a common practice nowadays to make use of GPU when training machine learning models, but it's not the case back then. Usually use CPU, but if you can use GPU, then why not? So they also utilize GPU in this model. Yeah, and there are lots of algorithms. There are lots of researches about machine learning. It's not just the ImageNet paper. There's the learning representations by backpropagating errors by Geoffrey Hinton as well, which is the foundation of neural networks, the backpropagation in gradient descent. And there's GANs, or generative adversarial nets. The example that I've shown you earlier about creating faces of people that are not real, but it looks real. So it uses GANs. Basically, if there's no papers, there's no research about AI, then we can't get here. So to summarize, the it's here. Yeah, what caused the AI resurgence are the following: there's data, hardware, and research. And here are the godfathers of AI. So Jan LeCun, Joshua Benge, and Geoffrey Hinton. Okay, so before I do like a crash course on machine learning, I think it would be best to differentiate AI, ML, and DS because I believe lots of people are confused with these terminologies. People usually just throw them everywhere. So here's a meme that I often see about machine learning and AI. So some people say it's just rebranded statistics. You know, you just reframe it and it becomes machine learning. And if you market it enough, then and lots of people will be um, listening to you if you brand it as AI. I partially agree with this. ML and AI is not just statistics; it's also math, CS, and other things. But yes, statistics is an integral component of machine learning. But yeah, you could think of it like this, I guess. You are just rebranding statistics, but with something else. You add more things. You add programming, you add CS concepts, you add other things. Yeah, I've already mentioned this. When you advertise, it's AI. When you hire, it's machine learning. When you implement, it's linear regression. Linear regression, by the way, is one example of machine learning model. Oh, I've already shown this slide before, but I want to emphasize again that um, machine learning is a subset of AI. In AI, it could be ML or non-ML based, as long as you mimic what we can do as humans, as long as it can perform something that you can do. For example, if you use a rule-based technique to determine something, then as long as it does the job, then that's AI in a general sense. It doesn't have to be ML. So AI is the bigger thing, ML is inside it. So that's the differentiation of AI and ML. Yeah, I'll just skip this. I don't think we have much time. What about data science? So to put it simply, data science is the science of finding patterns in data. And in data science, you make use of lots of things like computer science, math, statistics, domain, or business knowledge to um, help solve business problems. That's basically your goal in modern data science. So it's really applied. So you're using ML or other techniques to solve a business problem. That's DS or data science. Okay, still following?
Yes.
Okay, great, great. ML crash course. So let's start. So machine learning is the ability of computers to learn without being explicitly programmed. So if you see this image, what do you think is this? It's a cat. Yes, correct. It's a cat. Um, if you see this image, what is this? It's a correct. It's a dog. A doggo. And what about this image? It's a it's a cat. How did you know? How did you know that this is a cat? What's your basis? The shape, yes, correct. The shape. It seems like a cat. But how did you know that the first image is a cat, the second image is a dog, the third image is a cat? How did you know all those things? Because of the features, right? And what are the features of a cat? What are the features of a dog? How did you learn those features? Pointy ears, yeah, I agree. But I would say we know that this is a dog because we have seen so many examples since we were children, right? Yes, we learn them while seeing them as we grow. Through countless times seeing cat or dog. Yes, I agree with your statements. That is correct. That is correct. And this is very similar with machine learning systems. At first, it's dumb, like a baby. It's dumb at first. It doesn't know anything about the world. But as the baby grows, it will see lots of examples, and it will be able to learn those things. It will be able to differentiate what's a cat and a dog, and that's the same for machine learning models as well. You feed it with so much examples, you feed it with thousands usually of examples, until it learns that if it sees these features, then it's a cat or a dog or whatever, right? Great. Okay. So the good thing with learning machine learning is you could apply it to so many things. Although, I mean, it's not the end all be all, but learning it is a very powerful skill. For example, if you want to do natural language processing or NLP, many of the techniques that we're using there are ML-based, but not all. That's what I'm trying to point out here in this Venn diagram. If you want to do computer vision, you will be utilizing lots of machine learning as well, but not all computer vision are machine learning based. But if you know machine learning, you could do all these things. Basically, you could somehow do NLP, you could do CV with your knowledge in machine learning. And that's the power of it. It still helps if you know NLP and computer vision specific stuff. Yeah, here are some terminologies in machine learning. So when I mention them later, you won't get confused. So if I say label, this is what we're trying to predict for the output. When I say feature or column, those are the input variables. If I say row or sample, they're the particular instance of data. For the model, it defines the relationship between features and labels, and the metric is used to evaluate the goodness of our model. So there are different types of machine learning. There's supervised, unsupervised, and reinforcement learning. In supervised, you have a label. It is supervised. You have an input and an output. If this is your input, then this should be your output. That's what you're trying to do in supervised learning. Whereas in unsupervised learning, you don't have an output, you just have the input. And you're trying to infer something based from the input. For example, in here, we have cluster dimensionality reduction techniques. In reinforcement learning, it's basically, well, to put it simply, it's basically a simulation. You will set up the environment, and the goal is to get to a point where it will win. You try lots of simulations until it achieves whatever goal you put there. Unlike these two techniques, this is very customized. This is very complicated to implement because you have to set up the environment. So normally, when we do machine learning, in most cases, in most applications, you usually use supervised learning. This is the easiest machine learning. And for this discussion, I'll just be focusing on supervised learning. It's very simple. Like most of the applications that you'll see out there are supervised learning. So unsupervised is also often used. So, but yeah, supervised dominates the machine learning space, at least at the moment. So in supervised machine learning, again, you have your inputs and outputs. For example, X is your input and Y is your output. This is the convention that we typically use in the machine learning. So later, if you see some code and there's an X or Y, X means input, Y means output. And in supervised machine learning, you're trying to find this thing in between that will map the input to output, whatever that thing is, whatever it is. So if you see this example, 30, 65, and 100, and you'll try to convert it to 66, 143, and 220. What do you think is this thing in between that will convert the input to the output? Any hunches? And it's a simple mathematical expression. You just have to do something to convert this thing to this thing on the right. What do you think is this thing in between? It's a very basic operation. You'll have to perform. Okay, you have to do multiplication. So what do you have to multiply to convert the input to the output? Okay, so actually it's just 2.2. So it's kilogram to pounds. It's that simple. How about this one? If you're trying to convert 34, 54, 72, 93.2, 129.2, and 158, what do you think is this thing in between that will satisfy this? It's actually a bit more complicated. It's also a very common metric. I'll just show it. So it's Celsius to Fahrenheit. It's x times 9 over 5 plus 32. Right? A bit more complicated. So basically in supervised machine learning, we're trying to find this thing in between. But unlike those previous examples that we have shown, the ML model should automatically find it for you instead of us trying to figure out that this is the equation, this is the equation. We don't have to do that. We just plug in some machine learning model and it will find that out for you. Like we'd use KNN, linear regression, SVM, or neural networks. Could be any other machine learning model. And that's the power of machine learning models. Although there are caveats, of course. You use some machine learning models for a specific problem, but that's generally the idea. You plug in some ML model and it will find out that thing in between for you. And it doesn't have to be like numbers, as you can see here. It could be this, it could be an image, it could be a text. Although you have to do some transformation to convert them into their numerical format. Images are just numbers. Text, you have to do some pre-processing to convert it into numbers. And after that, you could turn it into a typical supervised machine learning problem. So yeah, this is a machine learning training in a nutshell. So this is a meme. Interview, what's your biggest strength? Me, I'm an expert in machine learning. Interviewer, what's 6%? 0. So at first you get it wrong. But as you do lots of iterations, you'll get there. So the second one is nowhere near nowhere near it's 16. Then me it's 16. Okay, what's 10 plus 20? So this is how machine learning models work. If it sees another example, it just bases it on what it has learned before. And unfortunately, in this specific example, it has only learned 16 because that's the only example that has been fed into it. And now it has seen an example, it doesn't know what to answer. So if you feed it so many examples, then it will be able to answer, well, hopefully answer different variations of the addition problem. But yeah, some prerequisites in machine learning. If you really want to deep dive in machine learning, you have to know programming, statistics and probability calculus and linear algebra. If you want to just apply it, at a high level, then I guess programming skill will do. But I highly encourage learning stats and probability. Then if you really want to deep dive in, learn calculus and linear algebra. Those are very necessary when we do ML, especially in deep learning. You'll see lots of possible errors if you don't know calculus and linear algebra. You don't know why those things are happening when it's not converging, when you're getting exploding gradient, diminishing, and whatnot. Helps if you know the basics. But programming skill will do in most cases if you're just gonna apply it. You just use the APIs. Yeah. Most people usually, just ignore the math stuff. But when you get to high level ML or deep learning, it will come back to haunt you. Like if you do graduate level machine learning, math stats, linear algebra, those things are very important in machine learning. So behind the scenes of in some of the machine learning models, you'll often see this. This is gradient descent visualized. So I won't be discussing gradient descent right now, but there's so many things happening behind the scenes. That's what I'm trying to point out here. You compute the distance, you make use of lots of algorithms, you cluster them and whatnot. But the APIs that we will be using, or I mean, if you use sklearn or TensorFlow, abstracts those things for you. And that is why I mentioned that programming skill will do in if you're just gonna do a high level implementation of machine learning, but if you really want to do dive, then you have to understand these things. You also usually deal with high dimensional data sets in machine learning. I'm not sure why this stopped moving. This is supposed to be a GIF. But anyway, it stopped moving. It turned into an image. So there are two types of problems in machine learning. There's classification and regression. I still have time. Classification and regression. In regression, you're trying to predict, they call this continuous values. Like, for example, if you have, say, 50 cricket chirps per minute, then it means the temperature is 10. So it's a continuous value, as you can see here. You can also try to predict like the monthly demand of electricity and also the supply. Those are regression problems. Whereas in classification, you are predicting the classes. Like, is this class 1, 2, 3, or is this male or female? Is this cat or dog? That's classification. And different machine learning models will have different ways of segregating your data. So what I'm trying to highlight here is that use different machine learning models for different problems. There should be a good machine learning model for your problem if it has a pattern. That's one assumption. So for example, here, if we try to make use of a linear model like linear SPM, and you have a data set that looks like this, like a yin yang, of course it will not work because it has some curvature. You have to capture that curvature, and there are better models for that, like RBF, SVM, and Gaussian process. Yeah, there are lots of machine learning algorithms. There's naive Bayes, K-nearest neighbors, logistic regression, SVM, decision trees, and neural networks, and use different algorithms for different problems. If you have a linear data, then you have to use a linear model, like linear logistic regression, or SVM, with a linear kernel. If you have an image data, then you have to use convolutional neural networks. That's like a given nowadays. We use that for image data. If you're dealing with sequential data, then it's best to use LSTM, although recently transformer-based models are becoming a thing, and it has replaced LSTM. But before, it's usually LSTM or recurrent neural networks. If you want model interpretability, then use decision trees, random forest, naive-Bayes, or linear models. Or if you want to do clustering, then use k-means, hierarchical clustering, or LDA. If what you're going for is just the maximum accuracy, then you might want to use ensemble algorithms or neural networks. In most cases, they will give you the best accuracy. So yeah, different algorithms for different problems. If you need a guide on what to do, given your data set, then you might want to utilize this cheat sheet from sklearn. Sklearn is one of the uh, libraries that we use in machine learning and then Python. So you start here. If you have less than 50 samples, then you have to get more data. Really need data when you do machine learning. But if you have more than that, then you identify the problem. Are you trying to predict that category or not? If you deal with categories, then that's classification. If not, it's regression. And you follow this arrows here depending on what you have. I won't discuss this in depth, but basically, when doing machine learning, you have to prepare your data. Then after that, you build and train your models, and then you deploy it. To put it simply, that's what we're doing. This is a very important part when doing machine learning. You have to evaluate it. You have to know how good your model is. And in evaluation, you usually split it into train and test set. There are better ways to do it. There's cross validation. There are other things to configure this, but this is the most basic setup. You just have train and test set. So in train set, you could think of it as studying for an exam. And test set, that's the actual exam. So you train your data here. I mean, you train your model here in the train set because that's studying for an exam. And then eventually you will test it in the test set. You will check if it still performs well in the set that it hasn't seen yet. And that's the actual exam. And you use an appropriate evaluation metric depending on your problem. So for example, if you're dealing with a classification problem, then you can use accuracy, precision, recall F1. If you're dealing with a regression problem, then you can use R-squared, RMSE, or map it. I can put it here, but there are lots of metrics. I have highlighted here accuracy and R-squared because those are the default ones being used by different libraries. So if you did not specify anything, it's going to be accuracy for classification tasks and R-squared for regression tasks. Yeah, so here are some common pitfalls in machine learning. So there's overfitting and underfitting. Overfitting is here, but memorizing the train set and performing poorly on the test set. So let's look at the right graph here. You try your best to fit all data points correctly, but as you can see here, it doesn't really capture the trend. There's so many curves, whereas this one in the middle is just the right balance. It captured the trend that it looks like a parabolic function, right? You don't have much parameters to model this data set that we have here. It's just a simple curve. Whereas in underfitting, you're just performing badly because you use an inappropriate model. Like for example, you use a linear model, but it's not a linear data set. So expect bad results. Okay, still following?
Yes, sir.
Okay, great. We still have time for the quick TensorFlow demo. Let's see. Let's finish this. Another example. This is for classification now. For example, you have two classes, circle and X. Use a linear model to separate the data. And you see that it has this curve here. Of course, it won't perform well because you're using a linear model for something that is not linear. If you use something like this one here that has a curvature, then you get an appropriate fit. If you try to like do your best to capture each data point, then you won't get the trend. Of course, you're gonna get perfect score here in the train set, but it doesn't really capture the overall trend. But it's just a simple like curve, as you can see here in the middle. So that's overfitting. It's too good to be true. So how do we do machine learning? Well, first is you have to understand the understand things at a high level. I suggest knowing the CRISP-DM framework. So what is the CRISP-DM framework? It's basically this, you have to understand the business and then the data. Then after that, you prepare the data. And once you prepare the data, you do the modeling. Then you do the evaluation. And then if that's not enough, then you go back and then you keep doing this until you get good results. That's the CRISP-DM framework. It's a cycle, basically. You keep on doing this until you get the desired results. So again, it starts with the business understanding and data understanding. I mean, you could do all the machine learning modeling you want, but if you're solving the wrong problem, then it's pointless. So you really have to understand why you're doing that to begin with. Another important thing when doing machine learning is doing exploratory data analysis. In exploratory data analysis, you usually just understand the data first before you do any modeling. You do some visualization to see something. Like in here, you could actually conclude something by just doing EDA. So it's a very important step because you need to understand the data before you do any modeling. But you have to know the characteristics of it. Maybe you don't even need to ML modeling at all. Maybe it's just a simple, I don't know, math or stat equation, and that will solve the problem. There's no need to complicate things. Oh yeah, I repeated this thing. Yeah, you also need to identify the ML problem. So is it a classification, regression, or clustering? Just to remind you, classification is picking one of n labels. Regression is predicting numerical values. Clustering is grouping similar examples. And here are different examples. And you start simple. There's no need to use the state-of-the-art neural network technique or deep learning technique. A simple machine learning model would do in most cases, and you'll usually get a good performance out of it. And then you just did it incrementally. If you get a better heuristic, then use that, and then you'll get a small increase in performance, and then keep on using the better models until you get the highest accuracy. But usually, those are just going to be marginal gains. So you just start simple. There's no need to overcomplicate things. Yeah, and we use lots of libraries when doing machine learning. So there's scalar, NumPy, Keras, TensorFlow, PyTorch, Matplotlib, and that's Python. So Python is, well, all these things are Python. And for this session, of course, I'm going to be focusing on TensorFlow, specifically Keras. Keras is a high-level API built on top of TensorFlow. But actually, in most ML modeling, scalar will do, and I suggest using scalar. It's very simple. If you have a very easy data set, then you just need 3 lines of code. Assuming that you don't have to do any pre-processing. Just need 3 lines of code and then you're done. That's how easy it is to train a model in scalar. Of course, this is a very ideal case. In most cases, it doesn't happen. You have to do something else in addition to this. So in addition to scalar, there's TensorFlow, and yeah, it's going to be what we're using for this session. So TensorFlow is created by Google Brain Team, and it's an end-to-end open source platform for numerical computation and large-scale machine learning. But more specifically, we'll be using Keras because it's a high-level API for deep learning, and it makes deep learning coding a lot easier than what it used to be. If you do things using just plain TensorFlow, there's so much code that you have to do if you're gonna do it the old way. But with Keras, it's just a few lines of code to train a deep learning model, and it's created by François Cholet, a Google engineer as well. So if you look at the documentation, you will see his name a lot. He developed this higher level API for deep learning. So it abstracts lots of things in TensorFlow. Yeah, here are some tips in doing data science or machine learning. You could look at Kaggle, Papers with Code, World Bank, towards data science, documentation. I highly recommend reading the documentation more than any other tutorials that you can see here. Documentation is usually the best. Or books. I recommend documentations or books. Yeah, some applications of machine learning, deep learning. So this is face detection. This is a very popular example. We also have real-time object detection. We do this with deep learning techniques. Yeah, I developed this last year. Yeah, more than a year ago. So you could also do this. Like I integrated all those things. I created a web application, then face detection, real-time object detection, and sensors to detect my temperature. So yeah, I combined all those things. We also do self-driving cars. This is more advanced because you're integrating so many things here now. We also do topic modeling. So what is topic modeling? You identify the themes and in your text data. We'll also do text generation, like what I have shown you earlier. Like a robot wrote this entire article. Are you scared yet, human? Yeah. Like what I have shown you earlier. This is also generated by AI. I won't be reading this. It will take so much time. But yeah, go through that. So how do you train a deep learning model in Keras or TensorFlow? Of course, that won't be the focus of this course because, I mean, this session, because there will be a workshop dedicated for that, but I'll just show you briefly how to do. I'm gonna reconnect how to do deep learning training using Keras for TensorFlow. Just a few lines of code. Quickly. Okay, can you see my screen again?
Yes, sir.
Okay, great. So how do you train? Well, first of all, you have to import the libraries. That's a given. You import TensorFlow, you import NumPy. Matplotlib is just for visualization purposes. You have to load the data. So it could be from any other source, but there's already a fashion MNIST dataset in TensorFlow, so I'm going to be using that. This is a very popular dataset for image classification. And here are different class names that we have for the fashion MNIST data. So you have t-shirt, top, trouser, pullover, dress, coat, sandal, shirt, sneaker bag, ankle boot. So here's a visualization of some of the images. Unfortunately, it's just grayscale or black and white. But yeah, you have an idea already on the data that we're dealing with through this plot that we have here. So here are the different images, and now we're going to train a deep learning model for this. Right. So here's the TensorFlow code for it, for Keras specifically. So this is the model that we'll be creating. We're going to create this neural network architecture, very simple feed-forward neural network. So you create 28 as input shape for your initial layer, and then 128 for the next layer, and then finally 10 because you're predicting 10 outputs. I believe this will be discussed in more detail in the workshop part later. But yeah, you have this simple line of code to do your modeling. So you flatten the initial data set first. So 28 by 28 is the size of your image, and you're going to flatten it. So it's going to be 28 by 1, 28 times 28. You're going to have that much features in your first layer, then followed by 128 and then. And then use Adam as optimizer, and then your loss is sparse categorical cross entropy. Then you're going to be using accuracy as your metric. And yeah, it will be training now. You have 10 epochs here. And then as you can see here, you have 0.9 accuracy. Actually, you can train this again. So you can see that it's really, really fast to train. It's fast, it's fast. It's fast. Look, you have 10 epochs. So epochs is one epoch is one pass in the whole data set. So you have this much epochs. 10 epochs. So you went through the data set 10 times. Yeah, just 4 seconds per epoch. Very fast. Initially, you get an accuracy of 0.82, and then it goes up as you increase the number of epochs. Of course, we don't want to add lots of epochs because it will be overfitting. Yeah, it will be a case of overfitting if we include so much epochs. And then you have to evaluate it now. At least in the train set, remember, you have train and test set, right? Train set is like study for the exam, and then test set is the actual exam. So at least in your review session, you have an accuracy of 0.91 here. But what is your actual score in the exam? We're going to be using the test set for that. And the test score here is 0.88 for 88%. Still good enough, near 91%. And yeah, you can predict, like, for example, we're gonna predict the first image here, and it's 9. We check the actual, and it's 9. So yeah, just to verify things, sanity check. So this is how we do deep learning training using Keras for TensorFlow. Of course, it's a very simple example. In other use cases, you might have to use, for example, a convolutional neural network model for more complicated images, because this is a very simple image data, 20 by 20, and it's just grayscale. And yeah, this is a very simple model. You could also use TensorFlow JS. So instead of using Python, you could use JavaScript to do deep learning. It's actually really cool because you could already make use of your models in your browser. I'll show some example here. Like, if you go to TensorFlow or the JS, you can see lots of examples. Like, what are good examples here? Maybe, yeah, I can think. Let's try this one. This is really cool. Though I think I will have to stop my camera for a bit because this needs my camera. Yeah, this needs my camera. I will stop my video for a bit. Wait. But you're still seeing it here. Sorry, it's taking some time, but yeah, this is me. So as you can see, yeah, you could already use those models in your browser because it's in JS. So if you know JS, then you could do these things. Like having a separate language for the backend, like Python, then you'll be using JavaScript for your frontend. You could just use JS all the way if you want. What else? There's also very, yeah, but you get the idea. You can do all these things. Sorry. Wait, let me stop. I'll start my video again. Where's my video? Let me go back. I don't think I have much time. How many minutes do I have left? Should I skip to the end? I would love to discuss the limitations, but I don't think I have much time. So I'm just gonna skip that part, I think.
You still have 5 minutes, Mr. Jude.
Okay, great. Just gonna go through it quickly. So just some limitations of AI and machine learning in general. I'm gonna share it now. So some limitations. This is called the unscums quartet. This example here. So what this means is that even though you have different data sets, if you make use of statistical aggregates, they'll all look the same. They'll have the same variance. They have the same slope, intercept. They'll have the same what else? Mean, standard deviation, all those things. So here's a good example of that. Very different graphs, right? Same mean, same standard deviation, same correlation, same everything, even though they're very different. So that is why it's important to do some visualization as well. Because you might get the same output even though they're very different. And also you have to be wary of some statistical biases. Do you know this example from World War II? This analysis that was done by a very famous statistician back then?
Yes, sir.
Yeah, the survivor bias, yeah. Good. Okay, great. So I'm just gonna explain it quickly. So basically the analysis here was that you focus on the spots that weren't hit by the bullets. because that means those are the planes that were not able to survive. And like, I mean, if you think about it normally, you will say, okay, I'll be enhancing these spots here that are in red because they've been hit a lot. But you have to think of the opposite. Those that did not survive are the ones hit here and here. And there's also concept drift. So basically the behavior of a system changes over time. So if you train a machine learning model now, wait for a few months, it might not work anymore. There's also curse of dimensionality. If you have so much features, then all your data points will look the same. So you have to use dimensionality reduction techniques. Yeah, some limitations. Basically, it's not able to understand concepts. It's at least for the large scale text generation models like GPT-2 or GPT-3, and it's very popular nowadays. It's just very probabilistic. If you input something like this, like 1 + 1, he'll get gibberish, like what I'm showing you here. But as humans, that 1 + 1 is equal to 2. But it's not used to this type of input. Yeah, I don't have time to discuss this. Yeah, some limitations in translation and also in image classification. So like this, did someone blink? It's hard. And then this, called this cupcake, and then the dog. It's hard to distinguish between the two. So those are some limitations of AI. Yeah, and finally, garbage in, garbage out. So don't expect good results if you have garbage input. Yeah, I won't be discussing this. Blah, blah, blah. Skip. But yeah, you get the idea. Thank you. Thank you.
Okay, we learned a lot from your machine learning talk. And also, TensorFlow is absolutely available to all the users around and ready for the development of any system on it. We will surely also to add AlphaGo to our list to watch. And just like what our CTO typed, data is really important now that we are embracing the fourth industrial revolution. Okay, for our absorbed crowd, here now is the time to ask question about the said topic. Okay, we have some questions already posted. So, okay, number one, have you experienced creating machine learning for a company, but in a long run, it did not go well or like not useful anymore?
Yes, definitely. For example, well, this is I'm sure they're still developing this right now. They're still continuing this. But there was a time when I was working in ADB. The our text generation model was performing good at first, and people's perception on what is good and what is not changes over time. So eventually, they think that the output of the generative model is not okay anymore because there are some changes in how they perceive things. So yeah, it isn't useful anymore. So we have to retrain it again, and that's very common. It's very, very common. Like the goal changes.
Okay, then as a beginner, what path should I take first to learn machine learning? Can you recommend some books, course video, or topics, or how many months for them to understand the concept of it?
I guess the good thing with machine learning is there are lots of entry points, I believe. Um, it depends on your background. For example, if you're coming from a CS, IT background, I believe you're already good in the programming aspect of things. So you should now learn about math and stat. If you're coming from like a math stat background, then you have to know about the programming side of things. So it depends on where you're starting from. And what are the books that I can recommend? A very practical book, I believe, for this is from O'Reilly. It's this machine learning using scikit-learn. I forgot if that's the exact title of the book, but it's from O'Reilly, and there's scikit-learn and like, TensorFlow and machine learning, I think, in the title. I'll look for it and I'll just type it in the chat. it's a good introductory book. If you wanna know like the basic concepts, I think Andrew Nang's machine learning course in Coursera is a very good introductory course, at least for the basics. And how many months for you to understand the concept? It really depends on your background. As I said, if you already have like a background in math stat, then you might have to learn the programming stuff. And if you have the opposite, then you have to learn the other things as well. So it depends on you. You can say. Uh, Other questions?
Yes. So make sure to take that a suggestion by Mr. Jude. Okay. How long will it take to train a certain model? Is it depending on the number of data, chosen model, or other reasons?
All of those things. All of those things. Like I have trained a neural network model earlier, and it took just a few seconds. And neural network is more complicated than most machine learning techniques. So it depends on the model. It depends on the data set. If you have something that is that small, like the fashion MNIST data set, it's quite small, and used like any machine learning model, it should be fast. It should be fast. I mean, neural network with just 3 layers took just a few seconds, right? So it should be fast. It really depends on many factors like number of data, chosen model, and other things, and the computer that you're using. So if you have GPU, then it's gonna be fast.
So they're also asking, what is the good percent of accuracy of a model?
Depends on the data set. Depends on the problem. What is a good accuracy? You usually look at a human benchmark if that is possible. So for example, if it is a task that is easily done by humans, then your goal is to get an accuracy that is near the performance of your human counterparts. If, for example, maybe the human experts are getting, say, 90%. What's an example of this that is quite relevant nowadays? Like the medical imaging, the X-ray imaging, and then it will predict if you have a disease or what. And doctors could say predict with 90% accuracy, and you're getting a model that is near 90%, then I would say that's a good model. But
Okay.
if the human counterpart is getting like 50%, then well, that's bad. But if the ML model is getting something that is near that, then I can blame the ML model because the humans also are not performing well. It depends on the problem.
So
But
where
usually the benchmark is human. Yeah.
yeah,
Go.
yeah. Okay. Where and how can we get irrelevant data?
Where you can get ideally you get it from well, in the context of a corporation or company, you get it from the stakeholders. You get it from the people who are really generating the data or like sensors. But for typical machine learning projects, if you just wanna play with ML and data science, then I suggest looking data in World Bank. I usually use World Bank data in my projects, or just go to Kaggle. It has so much data sets. But your question is relevant, and I think World Bank data is relevant more than like typical Kaggle data sets, wherein it's just for play in many cases.
Okay. Okay, then do you believe that artificial intelligence will take over a majority of the tasks of the modern world? What do you think?
Depends on the timeline. If we're talking about decades, then yes. But if what you're saying is like 5 years from now, no. We have so much to achieve in the AI field to get there. We're still far. But eventually, yes, that is the goal of AI, to copy us humans and make lives easier.
Yeah.
Yes.
Okay. Then how can we make machine learning more inclusive to other fields that we apply this, since there are perceptive problems on how non-computer science take machine learning?
Wait, I'm processing the question. How can you make it more inclusive? Well, I believe this field right now is inclusive compared to other fields. So I'm not, well, honestly, I'm not thinking this is a problem right now because, for example, in the data science field, you're using ML to solve lots of business problems. And in data science, lots of practitioners come from non-CS or IT backgrounds because you could start from lots of entry points. You could start from like a stat background and you just learn the things that are needed for the job and to make data science work in general. There's so many entry points, and that is why I think this field is becoming more inclusive because of that. Because you could start from lots of points and then learn ML along the way to apply it to whatever you're doing.
Okay, then do you think that machine learning tools will be so abundant in the future, making complex math somehow less relevant in the future, or same in big data because of the abstraction?
Honestly, I think math is okay. It depends on the role. It depends on the role. But for me, as an academic, math is more relevant primarily because ML tools are so prevalent nowadays. And what's going to be your differentiator with other players in the field if you don't know math? Because all of you are going to be using the same set of tools. So what's going to be your add-on if you all of you are just using the same tool, right? You have to have something else that will make you more relevant. So in that sense, I think math is going to be more important because there's so many abstractions. Like people just use those APIs blindly and not knowing if the model is really performing well or not. And that's where math and stat knowledge will come into play to determine if what you're doing is really correct with the abundance of MLPs.
Okay, for the last question, what is the percent of accuracy to be called as underfitted, good or robust, and overfitted?
It depends. It is overfitting when your train set is much, much higher than your test set. So you base it on the difference of your train set score and test set score. That's how you know if it's overfitting. Underfitting is simply the model not performing well.
Okay,
With
so yeah.
the scores.
Okay, that's it for this time. For other questions and unread messages, just send us a message on our Facebook page and we will forward it to our speaker later on. Okay. Mr. Jude, the Google developer Student Clouds Technological University of the Philippines, Manila, present this certificate to you, Mr. Jude Michael Teves, for imparting valuable insights in the event GTEC Summit 2021, Getting Grounded with Google Technology. Given this 11th day of December 2021 via Zoom web conferencing, signed by our GDSC lead and President Justine Nicole Barbe and our Chief Executive Officer, John Carlo Di Chotto.